We're now going to sketch the graph of a rational function. F of x is x squared divided by x squared plus 3. Just to make things easier, I already calculated the first derivative and the second derivative, so we can just focus on learning how to graph the function. Let's first look at the domain. We have to check if the denominator is equal to 0, because we have a rational function. X squared plus 3 cannot ever be equal to 0 because of the x squared term. So for the domain, it's going to be all values of x. So let's write down minus infinity to infinity. Let's now look at intercepts. We're going to start by finding the y-intercept because that's easier. To find the y-intercept, we are going to let x be equal to 0. So looking up at our function that I highlighted in yellow, if we plug in x is 0, we get that f is also equal to 0. So this tells us that our intercept is 0, 0, and that is both our x and y intercept. Now let's think about symmetry. To find the symmetry, we need to calculate f at minus x. So wherever we have an x in our function, we're going to plug in minus x. This gives us a minus x squared, all divided by minus x squared plus 3. And this is x squared over x squared plus 3, which is the same as f of x. This tells us that our graph is going to have symmetry about the y-axis. Now let's look at the end behavior. I am going to go ahead and rewrite our function because we can't see it anymore. It is x squared all divided by x squared plus 3. When we look at asymptotes, we want to see where the denominator is equal to 0. In our function, it isn't, so we have no vertical asymptote. But now let's think about horizontal asymptotes. When you calculate a horizontal or a slant asymptote, you need to look at the highest power in your numerator and the highest power in the denominator. Those two powers are the same, so that tells us that we have a horizontal asymptote. And to find what that horizontal asymptote is, we have to think about the limit as x goes to plus or minus infinity. We're going to do this really informally. F of x is going to look like x squared over x squared, because only the leading terms count as x gets really big. And this is equal to 1. So we can say that our horizontal asymptote is y is equal to 1. Let's now look at intervals of increasing or decreasing. To find increasing or decreasing, we need to take the first derivative and set it equal to 0, or see where it's undefined. Our first derivative from up above was 6x, all divided by x squared plus 3 quantity squared. It's never going to be undefined, but it is going to equal 0 when x is equal to 0. So if we set that equal to 0, we get that x is equal to 0. So we can go ahead and draw a number line, and we're going to put 0 on this, and we're going to look at f prime. We want to find if f prime is positive or negative. Notice that the denominator is positive, so we don't even have to think about that. We just have to look at the numerator. Let's pick a number less than 0, like -1, and we see that f prime is going to be negative, and then to the right, it's going to be positive. This tells us that our function is decreasing in this region and increasing in this region. We can say then that it is decreasing on the interval from minus infinity to 0, and it's increasing on the interval from 0 to infinity. Let's now think about local max and mins. Looking up at part E, you can see that we are going to have a min when x is equal to 0. So let's go ahead and let's write that down. We are going to have a local min at x is equal to 0. And we saw when we were doing our intercepts that f at 0 was equal to 0. So we can say we have a local min at 0, 0. So that's just a min at the origin. And from our graph in part E, we can see that we have no local max. So let's write down no local max. Let's now look at concavity and inflection points. For the inflection point, we're going to need to find the value of f at a point. So let's go ahead and write down what f is again. F is x squared, all divided by x squared plus 3. To find concavity, we need to use the second derivative. So let's write down what that is. That was given up above, and it is 18 times 1 minus x squared, all divided by x squared plus 3 quantity cubed. We need to find where f double prime is equal to 0. So this is just where 1 minus x squared is equal to 0. And this gives us that x is plus or minus 1. Let's now go ahead and draw our number line. And now we're going to put 2 points on it, minus 1 and 1. And we are looking at the value of f double prime. Because our denominator is always positive, to find the value of f double prime, we really just have to look at this term right here and see if it's positive or negative. If we let x be in this region, say x is negative 2, then f double prime is going to be negative. In this region, we could say x is 0, so it's going to be positive. And then in our right region, if we say x is 2, it's going to be negative. This tells us that our function is then concave down, concave up, and concave down in those regions. Let's go ahead and let's write that down. It is concave down in the region from minus infinity to minus 1, and in the region from 1 to infinity, and then it's concave up in the region in between, which is minus 1 to 1. We are going to have an inflection point at negative 1 and at 1. I'm going to come up here and look at our function, f, and we need to find what it's equal to at minus 1 and 1. Because we have an x squared, it's going to be the same value for minus 1 and 1. So f at plus or minus 1 is going to be 1 over 4, so 1/4. So we're going to have 2 inflection points. The first one is minus 1, 1/4, and the second one is 1, 1/4. Now let's go ahead and put all this information on our graph. I think the best place to start is by putting all the points that we calculated and put those on our graph. We found that we have an intercept here at the origin. We have a local min there. And then we have inflection points at minus 1, 1/4 and 1, 1/4. So minus 1, 1/4 is right here, and 1, 1/4 is right here. Now let's see what else we can add to our graph. We have a horizontal asymptote at y is equal to 1. So let's go ahead and let's put that in. And let's keep in mind that our graph is symmetric about the y-axis. Now let's look at increasing, decreasing, and concavity. It is increasing on the right side of the graph and decreasing on the left. And then it is concave up in between the two inflection points. So we're going to have concave up and then concave down. And that's it. It really helps to calculate all of this information first, and then it's pretty easy to graph the function.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.